Welcome back, everybody. So next we're going to have two junior talks. And these talks are going to be 20 minutes long. So I ask all of the people here to ask the questions at the end of the talk. And for the first talk, I'm happy to announce Myrla Barbosa from the Universidad Federal de Santa Catarina, and she will talk about the uniform algebraic rank.
Okay. Thank you so much. Thank you for having me today. It's on? Yes. It's always a pleasure to be here in IMPA and now for the first time talking, so I'm really, really glad. Also for seeing so many familiar and friendly faces. So today I'm not going to talk about the refinements of the uniform rank, sorry. I will be talking about only the variation of Caporazzo's algebraic rank, and I will give the second result that will be the existence and the descriptions of explicit Clifford representatives. So we know the classical Clifford inequality for smooth curves, right? You have an upper bound for the dimension of the space of global sessions for linear line bundles on a smooth curve. But this bound cannot be done in general when you have a reducible curve, okay? So you need some restrictions on the multi-degrees, and this is what we do when we try to get this Clifford representative. So let's just settle some notation for the theory of divisors on graphs. A graph for me would be a weighted graph, so I have a set of vertices, a set of edges, and a weight function, okay? The genus of this graph would have to be the first Betti number plus the sum of the weights in each vertex. And I will call a graph stable when for all of its vertices of weight 0, the valorization, the degree of the vertex would be bigger or equal than 3, and semi-stable when it's bigger or equal than 2, okay? So exceptional vertices for me are vertices of weight 0 and degree 2. So what is a divisor in this case? A divisor would be a formal sum of the vertices, and the multi-degree would be given when you take a fixed ordering of the vertices, okay? The degree would be the sum of all of the multi-degrees. And I will call a divisor effective when all of the multi-degrees are positive. I can define the canonical divisor of a graph, defining on each vertex as the degree of the vertex plus 2 times the weight minus 2. These will always have degree 2g minus 2. And I use principal divisors to define equivalence relation between two divisors. But I will always think of it as coming from one configuration to another using the ship firing moves. So lending and borrowing, okay? I don't think of principal divisors in general. And Baker and Urin defined what we call the combinatorial rank, which basically calculates how effective a divisor is. So how much effectiveness I allow to lose, let's say. And this definition was extended by Amini and Caporazzo for the case of graphs with weights and loops. And it doesn't depend on the representative that you choose on the class of the divisor, okay? I have Riemann for this graph, for this rank, I'm sorry, and I have Clifford's theorem. So I have a bound here for this rank using the degree of the divisor. But I would love to define an algebral geometric version for this rank. Now on curves, now on nodal curves. So what I would do is take the set of all of the nodal curves that have G as its dual graph. So I have vertices going to the components, the edges going to the intersections, and the weights going to the geometric genus of the curve. The peak of D here of the curve would be all of the line bundles that have D as its multi-degrees. But when I will define the rank, I have to be careful, because now I'm jumping from one representative to another. And depending on the representative that you choose on the class, this rank can explode. So by rank, I'm talking about the H0 of the line bundle -1, okay? So these two are in the same class, but this has rank 0, and this can be as big as I want, as large as I want when I allow M to go to infinity. And what Caporazzo did was defining what she calls the algebraic rank. Then here, I'm going to play with minimax, okay? So I start taking the maximum on all of the line bundles that have D as its multi-degrees. Then I'm going to take the minimum on the class. I cannot take the maximum, as we saw. And for last, I would take the maximum on all of the curves that have G as its dual graph. This rank has a lot of properties that we'll see reflected on what we call the uniform rank. But one of the first questions that we ask is that, is the minimax order really important, or can we change it? Okay? Can we change the minimax order? By doing so, meaning that now I will take the minimum on the class here, but for last, I get what we call the uniform rank. So these two ranks are only combinatorially, okay? You can think of it only combinatorially. The algebraic one is bounded above by the uniform one, okay? I don't need to use any, let's say, geometry for that. But are these ranks equal? Does it make sense to define this uniform rank? Because I already had the algebraic one, right? I know that the algebraic one is not always equal to the combinatorial. And this was the first reason why we asked these questions. But are these ranks equal? The answer is no. We just need this example here. So you have a graph, 3 vertices, and weight 0, weight 3, and weight 1. The Ci would be the irreducible component corresponding to Vi. So let's focus on V2, okay? So I have C2 here, a smooth curve of genus 3, that it can be only trigonal or hyperelliptic. Let's take 2 divisors here on the same class. When you calculate the Rmax for different curves of the same divisor, you get different Rmax. So for hyperelliptic, the Rmax would be 1, but when it comes to D, and for C2 trigonal, I will have Rmax 2, but for D prime, C2 would have rank 2, but C2 hyperelliptic will have rank 2, but when it's trigonal, will have rank 1. The game is the following. For one rank, I will take the minimum on the line, so I'll have 1 and 1. For the other one, I'll have the maximum on the column, so I will have always 2 and 2. When I take the minimum and the max, I have 1. When I take the maximum and then the minimum, I'll have 2, which gives us that if we would only calculate these ranks for these representatives, which we cannot, we have to calculate for all of them, we would have that the algebraic rank would be 1 and the uniform rank would be 2. And this is only combinatorially. Geometrically, what we do is that we have this theorem here that says that we just need to calculate these ranks for effective divisors. So the effective divisors will be the one realizing these ranks. And in this case, we have finite cases, and we can do the calculations and get that indeed this happens. So these are not the same ranks, okay? It makes sense to work with the uniform one. We have, as a summary, the inequality of ranks. So before, we already had that the algebraic one is bounded above by the combinatorial. Now we also have the uniform one is bounded by the combinatorial. As a direct corollary, we know that in the case that we already had that the algebraic one would be equal to the combinatorial one, we also have that the uniform will be equal to the combinatorial one. Just a parenthesis here. So there are cases, there were cases presented where the algebraic one, the Caporazzo's rank, was not equal to the combinatorial one. We worked on these problems and defined another rank. But unfortunately, for the same cases, the uniform one doesn't match, okay? So we don't have necessarily this equality always. Another result that we have is that people were really interested in the combinatorial rank when Baker and Orin proved the specialization lemma, right? So when you get a regular one parameter smoothing of a curve, what you have is that the rank of the generic fiber would be bounded above by the combinatorial rank, and the same result can be reflected by the uniform rank, just using the upper semi-continuity of H0, basically. Okay. We have Himaho for this rank. It's a classic, right? You define a rank and you want to know if Himaho works for it. And we have this corollary that tries to give you bounds or calculate when the rank it is exactly for semi-balanced divisors. Let's focus on items C and 2 because the bound here is really close to what we know as the Clifford inequality. And we have the Clifford inequality for this rank, okay? You can bound it by the degree of the divisor by 2 when the degree is between 0 and 2d minus 2. And now we get to the second part of this talk, which is the definition of what we call Clifford representatives. So this is a lot to ask. I would say I will call a multi-degree a Clifford representatives when every line bundle of this multi-degree on any curve with dual graph G satisfies Clifford inequality. So this is a strong ask. You need to prove that this makes sense, that you have cases where this happens, right? And we already know that in reducible curves, not all of the line bundles will have these properties. And this was first suggested by Caporazzo, Len, and Mello because they gave us this proposition that says that when the multi-degree has degree between 0 and 2g minus 2, for any curve, there exists a multi-degree, such that every line bundle with this multi-degree satisfies Clifford inequality. But this is not the existence of the representatives that we want, because each one of these curves could have a different divisor. I want all of the curves to choose the same divisor, okay? And this is our theorem, our theorem of the existence. We proved that when the degree is between 0 and 2g minus 2, any class of divisor will contain a Clifford representative, and this is used using the uniform rank. That's why these two topics are linked today. So the sketch of the proof is basically showing that the divisors that will realize the uniform rank, and by realize, what I'm saying is this, okay? I'm saying basically that the R alg of the G on any class, I don't know how to draw the deltas anymore, it's equal to GL. And this would be the R max of G. Or something like that. Sorry, this is a D. And one of the first examples that we have is the corollary of the Himaho theorem that we presented before. So when you have what we call semi-balanced divisors of degree 0 and 2g minus 2, those will be Clifford representatives because they are the ones realizing the uniform rank, okay? Okay, so now we can give explicit constructive descriptions of these Clifford representatives for a large class of ranks. I will call a divisor uniform when both the divisor and what we call the residual divisor are effectives. So all of the entries are bigger or equal than 2. Here, the residual is the canonical minus 2. The canonical, we remember that has degree genus minus 2. Okay? So the degree of this divisor will have to be bigger than 0 and between, 2g minus 2 minus d, something like that, right? the residual I was talking. And a divisor class is special when both the class and its residual class are effectives. And we will denote by GBR the graph obtained by G when contracting all of the edges that are not bridges. The bridges, because it's an edge that if it is a bridge, if I delete it, I will have a disconnected graph, okay? So when this GBR, it's a chain, meaning that it has no vertices of valency greater or equal than 2, I call it a chain of, not the GBR, the G will be a chain of 2 edge connected components. So in this first example here, this is G, and this is GBR, and this is a chain, right? But in the second here, the GBR, it's not a chain because I have here a vertex of degree 3. So it is not the kind of graphs that we want to work on. And to summarize, the descriptions of divisors satisfying Clifford inequality that we got was this one. So let G be a chain of 2 edge connected components, the graphs that we spoke just now. Okay. When for vertices of weight 0, I have that this vertex is adjacent to the loop, I can classify these Clifford representatives in this way. So the Clifford representative will be a uniform divisor when the class is special, will be what we call V-reduced divisors. These are the ones obtained by the Dark-Burney algorithm, okay? So you have an algorithm to find this divisor for each divisor that you have. When the class is not special and not effective, and will be, and then you take the V-reduced of the residual when the class is special and effective, okay? So future work, we would love to combinatorially characterize these Clifford representatives in any chip firing class constructively, not just their existence. And we would love to find promising type of divisors other than the ones that we already have. So yeah, that's it. Thank you so much for listening to me for 10 minutes.